Hi, I'm going to talk about permutations and combinations today. So a permutation is the number of ways you can sequence a certain number of items. If they're all unique, how many different ways can you rearrange those items and have a unique sequence? Combination is how many different ways can you just take a certain number of um, cards, for example. How many different ways can you have the same value? So if I wanted A's of 2, 3, and 4 in any order for a combination, notice a permutation is having it exactly that order. So A's 2, 3, and 4, that's a permutation, but a combination is having on A's 2, 3, and 4 in any order. I'm going to talk about how to draw those cards, how to figure out what the number of combinations are for that. If you just kept doing it, how many different ways can you do that? So I'm going to start with, see we have an ace, a 2, 3, 4, 5, okay? So we have this set of cards here. I have in reverse order. But we have an ace, a 2, a 3, a 4, a 5, and a 6, okay? So if we want to get all these cards in a sequence, we're going to have to draw first this card, then this one, then this one. And what we do is that's 1 and 6, 1 and 5, 1 and 4, 1 and 3, and there's 2 left, 1 and 2, and then just 1 left over, right? So I'm going to go through the math on how to do that, and then also just how to get a certain number of cards. Let's just say we want to pick 4 cards out. We want to get the ace to the 2 and the 3 and the 4. But there was out of 6 cards. How many different ways can we get 4 cards though? Because it may not just be exactly what we wanted. So to figure out the probability of doing that, we have to know the number of ways we can do it. And then the one set that we had, or if we use multiple sets in some other problem, we know at least what the denominator is. And that's the number of combinations or the number of permutations, whichever way we're doing it. I want to introduce to you the key real quick here. So n is the number of choices without replacement. So we have 6, and when we take 1 away, we only have 5, and we're not replacing the cards. Okay, this is in a casino. So that's what n is. In this case, this is 6. So n is 6 here. And let's say we're drawing only 4 cards, which is the example I give. So let's say we want to get an ace, 2, 3, and 4, either in order or out of order. That's 4. So k would be 4 in this example. X, here when I show it here, x is any number, quantity, or variable that represents a certain number, okay? That's what x is. I is each time, like which number am I drawing? So this is 1 or 0, whichever way you want to think about it. That's 2 or 1, that's 2 or 3 that I'm getting, and then 3 or 4. If we're starting at 0, then you got to subtract 1, okay? So now whenever you see a value with an exclamation mark behind it, the exclamation mark means factorial. What that means is we got to multiply each time we do this, and we got to use basically the cards that are left over. So at the beginning, if we're using 0, the cards left over after drawing no times is 6, right? 6. And then when we draw again, so let's take 6. This is 1 in 6 possibility of getting the ace, right? Because there were 6 cards. Now there are 5 possibilities, right, out of these cards. So if we take the 2, that was a 1 in 5 chance. There are 5 ways to do this. Before there were 6, so now there are 30 different ways to do this because we got to pick any card for either example. And we got to use the cards that are left over before we draw. So the next one, to get the 3, right, there's a 3, 4, 5, and 6. How many different ways can we draw this next card? That's 3. Or I'm sorry, that's 4. So to get the 3, that's 4. So now we have 30, and then 4 different ways to do that. That's 120 different ways, right? Now to get the 4, there were 3 cards. Now we multiply again, 3 times the 120 ways to do this, and we get 360. Now there are 2 of them. So to pick the next card, there's 720 ways to do it total, if you want to get the exact sequence, right? So now that's 720. It's deterministic as heck because you only got 1 card, right? So now, it's just one way to do that, right? So there are 720 ways to do this. Oops, I just dropped this card. Okay. So there were 720 ways to do this. That's 6 times 5 times 4 times 3 times 2. If you take that, you get 720. That's what factorial really means. We're just, whatever I is, whichever draw it is, we start with 0. So we take the number, divide it, or subtract 0, times that number again, minus 1 this time, then 2, then 3, all the way down to whatever it is, minus 1, so that we have a 1 at the end. You can do 0 if you want, because 0 factorial is actually 1, despite what makes the most sense. Because you would think if you started with 0, right, you take 0 times any number, you're going to get 0, right? But probability people like to think of 0 factorial as 1, because they don't want to erase everything they did before when they're multiplying. And so, like this book here, Probability for Dummies, by Deborah Rumsey, PhD, she says the way to think about it when you see 0 factorial is there's one way to arrange 0 items, and that's not to arrange them at all. When I read that, I felt a little bit like Rain Man, you know, when Tom Cruise cut the like, I don't know if it was 4, you cut them in half and it was all of a sudden 8 of the fish sticks, I think. I'm like, you know, whatever. But yeah, I guess whatever. If you want to think about it that way, cool. Whenever you see P and then like some value and then some value, you're taking this top value is not an exponent. It's actually the total number of whatever you had that you're drawing from, the total number, and then the B at the bottom there, when you see in this subscript, this is the superscript, that's a subscript. The subscript is the number that you're actually taking out of those numbers. So let's say we want to draw 4 cards. We want to get in this order or in any order. If we're drawing 4 out of 6, we have a 6 here, then a 4 there. So N is the number total, K is the number we're taking away, okay? And that's up to get a unique sequence. So whenever you see a P, that's permutation up here. That's a sequence, to get an exact sequence. Each time we're drawing it the exact right way, like I showed you here. For the blue ones, which are K, the red ones are N minus K, which is 6 minus 4, that's 2, the 2 left over, okay? Now, whenever you see a C in the same format, we're looking at the number of combinations. A combination is irrespective of the sequence. So let's say we want to draw 4 cards and it's an ace, a 2, 3, and a 4. It could be in the order of a 4, a 2, a 3, and then whatever's left over, the ace. Like, we don't care what order we draw them in, as long as we have those cards, we can rearrange them in our hand if we're playing poker. For example, we use 5 cards, but you don't care what order you drew them in when you took them out the pile. You only care about that you have those. That's a combination, and that's what C is. The mathematics for this are different, and I'm going to go through that and explain how it makes sense. So let's start out with picking all items and in a given sequence. So you notice I showed you some cards here, and I showed you an exact sequence. I actually kind of introduced that already. It's 1 in 720 to get all of them in the same order. You're taking 6 times 5 times 4 times 3 times 2 times 1, right? That's the math for this, because each time you have choices, but you have fewer choices each time. That's why when you see an exclamation mark, that means exactly this. But in probability, let's just say we only want to draw 4 cards, right? Well, we still got to go 6, 5, 4, and 3, but we don't care about the other 2. So if we're going to use N, exclamation mark, which is N factorial, we still got to divide the other 2 out, because there are only 2 ways to rearrange these. Now let's say we drew 7 cards. So let's say I have a 7 in diamonds and I threw it in the stack also, right? So now, if we're still drawing 4 cards, how many cards do we have left over? If we have 7 cards, we have 3 left over, because we drew 4 and we got 3 left. Looking at the 3 cards we didn't draw, right? But still comparing it to what we already drew, if we drew all 7 of them, we have those other 3 cards. They could be in any order and we don't care. Well, if we're going to figure out mathematically, we want to at least first figure it out if we drew all of them, because we care about the sequence. So if we just go through the sequence for all 7 of them, that's like 1 in like 5,040, I think is what it is. That's 7 factorial. 7 times 6, 5, 4, 3, 2, 1. If you multiply all those together, you get 5,040. So this is what this would look like. We only care about the blue ones, but to figure this out, if we want to simplify it, because remember, we got to still multiply from the highest number that we have, which is n. And then we got to keep going down and stop where we're not drawing. So the red ones are the ones we didn't draw. So we have the 1, 2, 3, 4, or this is actually an ace, but we have those 4 cards. How many different ways can we rearrange the ones we have left over? Well, I already told you there's only 2 ways to arrange a 5 and a 6. 5 and 6, or 6 and 5. Those are all the outcomes to get exactly ace, 2, 3, and 4. But if we want to use 7 cards, notice that we have 3. There are more ways to rearrange them all of a sudden, because you can have a 5, 6, 7, 5, 7, 6, 6, 5, 7, and so on. And to prove this, this is 1, 2, 3, 4, 5, 6. There are 6 ways to do this. To prove it, you can look, and each one you can see a 5, a 6, and a 7, and no duplicates. And you know that there's 3 cards, and those are only 3 left over, and there are only a 5, 6, or 7 in each of these. So I just proved to you that there are 6 ways, and exactly 6 ways to do this, if you want to get exactly this. Because remember, this one is the one we're choosing, but we have left over. We can only have these for your outcomes. And this is n minus k. So we start with 7, we drew 4, 7 minus 4 is 3, right? But we've got to do 3 factorial to figure out all the different ways we could have these cards, if you want to think about it this way. And this is how it works in math, because you basically want to eliminate the part on the right if we're only drawing some of the cards. We don't care about the other multiplication. When we do this, 3 factorial is 6. So there are 6 ways to organize those cards if we're doing 7, for example. And what is 6? Well, 6 is 2 times 3. So imagine a 7 on the left of the 6. 7 times 6, 42. 42 times 5 is what, like 210 times 4 is like 840 times 3 is like, I don't know, like, alright, I kind of got lost here. I think it's like 2,400 plus 4 times, okay, I'm sorry, I need to calculate. So we take 7 times 6 times 5 times 4 times 3 times 2 times 1. If we do that, you can also just use the factorial function, which is also here. You can press shift and then the little x and the exclamation mark after you type in whatever number it is, which would be 7. If we do this, we get 540. I'm sorry, 5,040, like I said before. So when we do this, that's the total number of possibilities. But now let's say on my calculator I already typed those in. I'm like, oh wait, I didn't want to put in the 3, the 2, and the 1. So I divide by 1. You still have 5,040, right? You divide by 2. You end up with like 2,500 plus 20, 2,520. You divide that by 2. And when you divide that by 2, you get, I think like, let's see, 7 factorial 50, 40, divide by 6, you end up with 840 possibilities if you're using 7 cards. Now, how do we put this into a formula? Well, we can take this. So first we do the 6, 5, 4, 3, 2, 1. So just imagine just like that, if we're just doing 6 cards. 6 times 5 times 4 times 3, we stop. We got to divide by the ones that are left over, which is n minus k, because that was the number we started with. And then we got to subtract out the ones we already took, so whatever's left over. If we do that, and then we look at all the possibilities, this formula comes out to n factorial divided by n minus k. 6 minus 4, that's 2, so divide 2. From the 720, because we did 6, that's 720, we get 360 to get the ace, the 2, the 3, and the 4, okay? And if you want to break it down this way, in this format, that's n times n minus 1 times n minus 2 times n minus 3, okay? And then we forget about these for a second, but we still divide them out as a factorial. So we end up with 360. What we're doing is we're taking all permutations, all sequences to get all 6 of them. Then we're dividing out the other 2 cards, the different ways to arrange those 2 cards, or in the 3 that would be 6 because it's 3 factorial. If you go up beyond that, that's 20, that's 6, and then 24, and 120. You just keep going, and you get the different values. So if you divide those out, this is the formula. So if you have 6, and we're drawing 4 to get an exact sequence of A's 2, 3, 4. We're taking this formula, which was the permutation that I talked about up here, to get an exact sequence. That equals n factorial, which was 6 factorial divided by 6 minus 6 minus 4, and that gives you the 2, so n minus k, and k was the one on the bottom here. And then you get the 360 after you do the factorial and the division. So that's for an exact sequence. Notice though, when we talked about these here, we didn't care about what order they're in. And the next part we want to talk about is combinations. So how do we figure out how to do something where we don't care about the combinations? Well, we're going to have to basically remultiply all the different ways to reorganize them, because that's what we did here, and it's pretty sound math, okay? So I want to at least kind of prove this to you by at least showing it one way and then another way and how we get the same number, okay? So for combinations, if we use the C, that's the number of combinations we can get. It doesn't matter what sequence it's in. We're drawing, out of 6 cards, we're drawing 4, right? But we don't care if it's a 1, 2, 3, or 4, or a 2, a 1, a 4, and a 3. We don't care about the order. And we also don't care about the order of these cards, which I'll get into in a little bit. So we use the same formula. If you just look at this part, this is to get the exact sequence of 1, 2, 3, and 4, or A's 2, 3, and 4. But there are many ways to arrange those 4 cards. There are exactly actually 24 ways to arrange an A's 2, 3, and a 4. And we already went over the math of that because we use factorial to figure it out. But we'd be starting over here, 1, 2, 3, 4, right? So, but we were drawing out of 6 cards, right? So what we did is we got fancy and we went 6 times 5 times 4 times 3 times 2 times 1. Then we divided out what was left over, which was n minus k. We took these 2 out and we ended up with 360, right? There are 360 ways to get these cards. This is 1 in 360 possibilities to get 1, 2, 3, and 4. But now we're going to multiply that times the number of ways we can get this, which is 24. But we're actually dividing because we're actually finding the number of combinations, not the probability. The probability would be the inverse of this value, which would be 1 over 360. So to figure out the number of actual combinations, we end up with 15 because we're taking 720 divided by 2 times the 4 again, because that's these 4 cards. How many different ways can we arrange this? We got to take 4 factorial. So 4 times 3 times 2 times 1 in the denominator here. That ends up being 24. This was 2. That's 48. If you divide 720 by 48, you get 15 combinations. And that's the math for this. So there are 15 ways to get these 4 cards out of the 6 cards. That's not, at least for me, that's not really intuitive, because I would generally think, if we're not caring about the order, that's 2/3 of the cards, right? So A's 2, 3, 4. I mean, it's 2/3 of the cards. But just to only get these 4 cards exactly and none of these cards in there, that's still 1 in 15. Now, when you're playing poker, think about that. And we're playing like at a casino, think about the fact that it's that improbable even. That's like 1 in 7, just a little bit above 1 in 7. Or just a little bit, above 1 in 7, or below 1 in 7, because 14% is 7. There's 7 14s in 100, basically. So that's still not very probable to actually get all 4 of those cards in any order when you're drawing them. So that's why math is kind of important. Math will really help you in our world, especially with companies trying to cheat people, not give you your benefits. You know, if you want to like get your drug or whatever, you gotta have the hassle with insurance companies and stuff. Really think about this though, like how many different ways can they tweak stuff to make it so you don't really get what you should get, even though they're using like, you know, customer service representatives and different other ways to just make it just a little more improbable. You don't get what you want, maybe 50% chance you'll actually get to like a manager, which is probably a joke, but whatever. But if you really think about it, they have different ways of doing things where you're just, there's a lower probability of you doing something. So math, they say, you know, math doesn't matter when you grow up, but really? Are you sure? Because people are using math to basically screw you, you know, if you really think about it. There are different ways to do things, and they know like the probability of you actually doing the exact right thing, getting the right sequence and doing exactly what you should do, so that they're checkmated if they don't do what they're supposed to do. And they do this stuff. They do the math and they figure out how to basically screw you. Okay? So I actually think math really matters, and you should really think about what I'm saying here. By the way, whenever you see a green around something, that's an actual formula. So that's the formula for an exact permutation. When you see green here, and I didn't really circle this, but that's the exact formula to find out the actual combination. Let's think about a different way to think about what I just said. Okay, I have 5 minutes left here. So let's just say we look at this, let's reframe the problem now, instead of multiplying this and this. Let's just say that you have these 6 cards, okay, and you still want to get the A's 2, 3, and 4 in any order, you don't care. So let me shuffle these cards up. Well, actually, I probably shouldn't shuffle them because I should have picked 2 cards that are specific. But let's just say I happen to pick the 5 and the 6. We don't care about what order they're in. But for now, we don't also care about the order these are in. So let's just say I picked the 2 cards and they happen to be a 5 and a 6 in any order, right? We already know if we took the 5 and the 6 out, we have the A's, the 2, the 3, and the 4 in whatever order we have them in, right? And that's the real thing we're trying to figure out here. So if we do that, let's just break it down to getting a 5 and a 6 in any order, right? We don't care. But to start out with, because remember n includes all of them, and we are still drawing out of all 6, let's use the sequence like we did up here implicitly. So let's just say we took the 2 cards, we did 2 draws out of the 6. So the probability of getting a 5 the first time is 1 in 6, because there were 6 cards. The probability of getting a 6 is 1 in 5. So 5 times 6, that's still 30, right? The 30 ways to just get exactly one sequence. But remember, we don't care what order those are in. So how many different ways can we rearrange this? Because if we can figure that out, and we're dividing it out of the number of ways to organize all 6, we already know, kind of like with this, except imagine that these don't have to be in this order. But as long as we look at this here, that was with 7, we don't care what order they're in. We know that these 4 cards are the ones that we want. That's the combination we're looking for. Because remember, this is not sequence specific. But we got to start with the sequence to use n like we want to use it, okay? Like the factorial. So first, we want to take 6 cards, because we're taking out of 6. We want to take those 2 cards that we don't care about, but right now we're caring about them. So that's the 5 and the 6. And then we want to figure out how many different ways we can arrange those 2 cards, the 5 and the 6. Well, there are 2 different ways, because we only have 2 cards. That's 2 times 1, because we're looking at the factorial, right? If it was the 720, like I showed you, that's 6, because it's 3 times 2 times 1. But in this case, it's 2 times 1. Remember the formula for that? The formula was this over here, because it's an exact sequence, right? But we want to know how many different ways there are to arrange. If we're just taking out 2 cards, and we're drawing 2 cards also, how many different ways can we do that? Either way, right? So we end up with, we take 2, 2. What we're really doing if we're looking in the context of this formula that we already used, n minus k was the 2. And I lost that minus. So, yep, I'm going to read marker, but that's a minus right there. Okay, that's 2. So we're taking 2 and 2. So we're doing permutation of out of 2, we take 2 cards. That's the same as 2, 2. So what this breaks down to is n minus k, because remember n minus k, that's the 6 minus the 4, and then we're taking the 6 minus the 4 out. When we do this, if we put it in this formula, n minus k over, and remember n was n minus k, and here, because we're looking at another example here, but using the same format, n minus k, and then minus, what was k again? K is also n minus k, right? So n minus k minus n minus k, if the n minus k is in parentheses for each one, you subtract and we end up with 0, because the same quantity minus the same quantity is 0. Then we're going to do factorial. Remember what I said about 0 factorial? Well, probability people like to say it's 1. So now, what we're doing is n minus k minus n minus k, so we end up with 0 factorial here, and we end up with 1, but up here in the numerator, in the denominator, we had n minus k, because we're dividing, taking 2 cards out of 6, over taking 2 cards out of 2 cards, and we end up with this formula here. And then when we simplify it, the n, which was 6n, and then the 2 is the same as n minus k. We take n minus k. These n's cancel, and the minus is times the minus of k. That's k. So we end up with n k. And when we do the math, we simplify it, we end up with the same formula we ended up with there. So basically, I've just showed you both ways of doing this. And when you do it either way, you still end up with this formula. Because n divided by k, you can actually move what's in the denominator up to there, because any number over 1 is itself. So just take the n minus k and move it up. You end up with n minus k times k factorial, which is exactly what we had here, because this is minus. And then you get the same formula. So it doesn't matter which way you think about this. I've showed you different ways of looking at this and finding the same formula. So I hope this helped you at some point believe that these formulas make sense. And I think probability does matter in our world. And I hope you think a lot about it and look at real life problems, and I hope you try to make a difference in our world. Thank you.